All right, so hello everyone. So my name is Jonathan Psaila, and welcome to my presentation for human-computer interaction. So the focus of my research throughout the course has been intelligent emotion recognition for human-computer interaction. And in this presentation, we're going to do a comparison of techniques of the 3 journal articles that I researched throughout the course. So to start off, here's a brief little table of contents. We're going to talk about what is emotion recognition, so we know where we are and where we're going. Then we're going to outline the 3 articles that I investigated, these being interpretable emotion recognition using EEG signals, robust representation and recognition of facial emotions using extreme sparse learning, and the spatial temporal recurrent neural network for emotion recognition. Then we're going to talk about the differences between these techniques, and as well as compare advantages versus disadvantages, and then conclude by talking which one of these 3 investigated methods is best using HCI principles. So to start off, what is emotion recognition? Well, the technical definition is emotion recognition is the process of detecting and recognizing a human emotion by a computer. Now, the hope is to use the recognized emotion to create a more fluid and efficient human-computer interaction interface. So with this, if research progresses, we could have a plethora of new technologies that could leverage this technology for the betterment of humans. So examples are advanced tutoring systems, advanced recommender systems, mental health initiatives. So much could be done if this is implemented correctly and accurately, I should say. So to start off, interpretable emotion recognition using EEG signals is the first topic we're going to discuss. So to start off, as I'm sure you're wondering, what is EEG signals? So an EEG signal stands for electroencephalography signals. And basically what these are is they are signals which are collected by placing electrodes on a person's head and measuring the amount of brain activity in the different cortexes. The thought being with this approach is if we can analyze the brain waves of people, then we can determine what emotion they're feeling in a given instant. So to start off, this scheme aims to classify a broad range of emotional categories. So these not being specific ones like happiness or sadness or anger, but more things like positive, negative, or calm emotions. So 2 data sets are used, these being the DAP and SEED data sets, and 5 features were extracted from the EEG signals in 1-second segments from each. So the first and second differentials and their normalized counterparts, and the differential entropy. Now in this little figure that I have at the bottom, this shows the placements of those electrodes on a subject's head in order for this scheme to be used. You can see that it's quite excessive with 62 electrodes that need to be connected at one point. Now, to conduct classification, we pass those features through 3 distinct classifiers and then use a softmax voting strategy to determine our final output. So the first classification scheme is a decision tree, which basically has a collection of individual feature values that we can traverse in order to finalize our, in order to get our final classification result. So in this little example right here, for instance, we have, car versus SUV. In this case, it would be a learned approach. So we would have a particular value here based off the first differential, for instance. And then down here, we'd look at the value of our second differential and then progress down the tree like that until we get one of our 3 emotional categories. For k-nearest neighbors, this middle one right here, what we effectively do is we plot our observable data and we determine which samples are closest to this data. And depending on a max strategy using the k-nearest neighbors, we say, okay, this unknown data sample belongs to this class because it's most similar to these k neighbors around it. And then lastly, the random forest method is using a collection of decision trees which use a different collection of those features in a particular order to then determine an output. With random forest, it then uses a majority voting strategy to output the final class. And using the results of all these 3, as I previously said, we use a softmax voting strategy to determine our final output. So based off the results of the training, 3 coefficients are found for each class, these being a correlation, an entropy, and weight coefficient. So the correlation coefficient effectively shows how correlated segments are in each sample based on an individual classification result. What this effectively means is when we have a sample that we know is a positive emotion, when we extract those 1-second segments from it, how similar are they when we have these varying segments that which we amalgamate together? Our entropy coefficient gives a measure of how much noise and change is present in an observed class when there are plenty of misclassifications. So once again, if we have a segment which we know is positive, and we take those 1 second segments, how much change occurs between the given segments? So these correlation and entropy coefficients, one is effectively saying, hey, how similar are they? And the entropy coefficient gives a measure of how different they can be from each other. Now, using these two pieces of information, we then construct our final coefficient, which is the weight coefficient. And this is calculated using the entropy and correlation coefficients for each class to fine-tune the system and optimize the scheme. So what this weight coefficient effectively does is when we have an observable sample, we use the weight coefficient to sway our results toward a particular class if we have a similar correlation or entropy coefficient that we can measure throughout our classification scheme. So here are some results for us. So using the last 34 seconds for the DEAP data set, we achieved an accuracy of 62.63%. However, for seed, using the last 75 seconds, we had an accuracy of 74.85%. Now, this was acquired not using the weight coefficient. When we do use the weight coefficient in this bottom table here, we see that accuracy increases. Now, although the accuracy jump isn't super substantial, only in the realm of about 0.15% or 0.5%, my apologies, it's still significant. It's also important to note, as you'll see in later slides, that the processing time here was quite fast, with a time of omega NP notation, based off the slowest classifier, which was the k-nearest neighbors classifier.